Continuing on to our second part here, following up on accuracy and precision, we can also look at classifying errors into two broad general types. First of all, we have what we call random errors, and random errors have essentially equal probability of being low or high, hence the term random. And in theory, when we are going ahead and estimating our last digit of a measurement, that should be a common random error because we are estimating, we don't know the value exactly, so we should be just as likely to estimate too high as too low. And systematic errors are errors which occur in the same direction each time, so they're always high or they're always low. For example, let's say you have a balance which is miscalibrated in some way and is always giving you a result which gives you a mass which is too high. So that would be a systematic error, and it should be essentially fairly easy to fix that kind of a systematic error. It's just a matter of recalibrating the balance. So consistent in terms of the way that that error shows up. If we go ahead and consider our bullseye diagrams again, we can see how the errors can be classified just like we did for accuracy and precision. So in the case of the diagram to the left, we're seeing large random errors. There's no real pattern to them whatsoever. They just seem to appear to be random strikes. On the diagram in the middle, on the other hand, you'll notice that the person is consistently hitting around the same area here. So the error is systematically too high up to the right and to the right. And then there's small errors because they're not consistently, random errors because they're not consistently hitting exactly the same spot. Same general idea over here in the middle. If everybody was hitting exactly right in the same spot, then there wouldn't be any random errors. But there are still some small random errors because the darts are hitting slightly above, slightly below, although they effectively cancel each other out almost in this case. So, and there's no systematic error here, not too high, not too far to the left, too far to the right, etc. We now move on to what is a vitally important topic in chemistry measurements, and that is the topic of significant figures, also called significant digits. So we've already defined that as being all of the certain and the one uncertain digits in a measurement. So what if you're given a series of measurements and you need to interpret them for determining significant digits? Well, there's a series of rules that we can follow. So first of all, any digit in a measurement which is not 0 is considered to be significant. So the digits 1 through 9. So the rules mostly focus here on zeros. So any 0 which comes at the beginning of a number is not significant. Any 0, and we call those leading zeros. Any 0 in between non-zero digits, including if there's more than one of these zeros, those are always considered significant. And zeros at the end of the number, this can be handled a little differently. What we would say is if there is a decimal point in the value that's reported, then those zeros are significant. Otherwise, we will treat them as not significant. Technically, what we could say is that they are ambiguous, but to keep life simple, we're just going to go ahead and say that they are not significant. So let's take a look here at some examples. Okay, I'm going to write out some numbers here. So let's try this number real quick, 19.5. How many significant digits are there? Well, all of those numbers are non-zero digits, so if we were to go ahead and write that down, we would say that all 3 digits are significant, every one of them. Let's try a few more. So how about this? 17.00, 1002, 0.0875, and 103.0, and 100, written like that. Okay, go ahead and pause the video for a moment and identify all the significant digits. And we'll resume in just a second. Okay, let's go ahead and take a look at these numbers and figure out how many figures we have. So in 17.00, of course, the non-zero digits are significant. These trailing zeros that come at the end are significant because of the presence of the decimal point. What that is essentially telling us is that this person was using a measuring apparatus which allowed them to be certain to the tenths place, so they were able to estimate their uncertain digit to the hundredths place, so all of those digits are significant. Okay, 1002, the 1 is significant, the 2 is significant, they're both non-zeros, and the zeros that come in between non-zero digits are significant. So we have here 4 significant digits. I didn't write it down here, but 4 significant digits on 17.00. The next number. These zeros come before the first non-zero digits. Of course, the non-zero digits are significant. Okay. This 0 is not significant because it's leading. It comes before the first non-zero digit. And now be very careful here. This 0 is still a leading 0. It comes before the first non-zero digit. So it is also not significant. In other words, what we could always do in this kind of a scenario is simply rewrite this value in scientific notation. And those zeros simply disappear. Okay? So those zeros are not significant, so we have in this value 3 significant digits. And you notice that regardless of whether you write the value in scientific notation or not, you must end up with the same number of significant digits in the value. 103.0. Well, the 1 is significant, the 3 is significant. The 0 is trapped between those, so it is significant. And then the trailing 0 in this case is significant because of the presence of the decimal. So we have 4 significant figures here. And then in this very badly written value, it's very ambiguous. We know the 1 is significant, but since there's no decimal place at the end of the number, we can't really say that either of those zeros are significant. They're totally ambiguous. So there's only 1 significant digit for sure here. Now, let's take a look at how we apply these significant digits to calculations. So we have a few sets of rules. One set of rules for multiplying and dividing, a set of rules for adding and subtracting, and then a set of rules for logarithms. So we'll start off with the multiplication and division rules. So this is fairly simple. What we do is we look at any measurements that we have, identify the number of significant digits in all the values being multiplied and or divided, and then what we do is we determine which one of these has the least number of significant digits. That is the number of significant digits your final answer will have. So if we go ahead and compare these two problems, we should be able to see quite easily how this is applied. So when we look at 4.50, that has 4, the 5, and the 0 are significant, so 3 significant digits. 2.81 has 3 significant digits. So we will round the final answer to the smallest of these, well, 3 or 3, 3 to 3 significant digits. And we'll go ahead and do that calculation in a second. On the other hand, if we look at these two measurements here, the first one has only 2 significant digits. The second value still has 3 significant digits. So the lesser of these, 2, is the number of significant digits which we must have in the final answer. Go ahead and calculate those results, and then what we're going to do is we will go ahead and see if you get the correct answer. All right, when you put this calculation into the calculator, what you get is a value of 12.645. So that's your calculator. So we decided we needed to round that to 3 significant digits in the first answer. So the first 3 significant digits, 12.6, and then we look next door to the 6 is a 4, which tells us we round down, or we just leave it alone as 12.6. So we have 12.6 as the value, and centimeters times centimeters gives you centimeters squared as the unit. Now we're going to do that over here for the 2 significant digits, 12.6, so the first 2 digits that are significant, 1 and the 2, and then adjacent to the 2 we have the 6, which tells us to round the 2 up. So this would be written as 13 centimeters squared. The rules for addition and subtraction are substantially different, and so it's very important not to mix up the multiplication and division rules with the addition and subtraction rules. So what we do is we're going to round to the decimal place of the least precise measurement. In other words, what you do is you look at each measurement, compare the last significant digit. So in 12.45, the last significant digit here is in the hundredths place. 3.12, the last significant digit, is also in the hundredths place. So in this particular case, what we're going to do is we're going to round our final answer to, unsurprisingly, the hundredths place. It has nothing to do with the fact that this number has 4 significant digits and this has 3 significant digits. We don't take that into account at all. So 14.25 minus 3.12 is going to be 11.13. And the unit in this case would be milliliters. If we go ahead and look at the problem to the right, you'll notice that we're going to the tenths place here, and we're going to the tenths place here. So we're going to round our answer to the tenths place. So in this particular scenario, we would have 11.2 mLs. Now, let me give a problem where they don't end in the same decimal place. So, for example, let's say we had 17.32 mLs plus 1.1 ml. The first number goes to the hundredths place, but the second value only goes to the tenths place. That is less precise. The tenths would be less precise than the hundredths. So we have to round our answer in this particular case to the tenths place. So if we carry out that addition, we get 17.42, but we now need to round that, we said, to the tenths place. So the way the answer should be represented is 17.4 milliliters. When we're using powers or roots, we're going to generally follow the same rules as for multiplication and division. So in this particular scenario here, we have 2 centimeters squared. Well, that's the same as 2.00 centimeters times 2.00 centimeters. So since it's essentially multiplication, it makes sense that we would follow the multiplication rules and get 4.00 centimeters squared. A root is essentially derived from multiple multiplications, so it should make sense then that if we're taking a square root or cube root or what have you, we will typically go ahead and use the multiplication and division rules. So 3 significant digits here, we end up with 3 significant digits in the final answer. The rules for logarithms are probably new to you. We don't typically cover those in introductory chemistry classes, and we often do not need to apply these rules until we get into the second semester of general chemistry, where logarithms start to come up fairly often. Okay, so the rule is generally this. When we're taking the logarithm of a value, you want to go to the same number of decimal places as there were numbers in the value here, significant digits in the value here. So if we're taking the log of 16.5, there are 3 significant digits here. So if there's 3 significant digits here, then that means we are going to go to 3 decimal places in the answer. On the other hand, if we have 2 decimal places, 2 significant digits here, then that means we should go to 2 decimal places in the answer. So when we take an anti-logarithm, in other words, you're going to take 10 to the power of a number, you just round the final answer to the same number of significant digits as the value have digits after the decimal point. So in this particular number, we have 3 digits after the decimal point. So we are going to round our final answer to a total of 3 significant digits. So 3 decimal places, 3 significant digits. If we look at this number here, we have 2 digits after the decimal point, so that gives us a total of 2 significant digits in the final answer. Now, it's vitally important that when you're doing your calculations, you want to avoid rounding, especially when you have a series of many steps in a calculation. What happens is, as you're carrying out multiple steps, every time you round, you're introducing a little bit of an error. And as you add yet another step and you keep adding more and more steps, you're adding further and further errors. So we want to try to keep those errors down as small as we can. One solution that people might have is to just simply keep all the calculations in the calculator, and that works well for multiplication and division. But if you have a mix of multiplication and division problems with addition and subtraction problems, that can get a little bit tricky. So the way that I recommend handling this is using what I call overbar notation. This is not brought up in the textbook. It's often introduced in more advanced analytical classes, but it works fine for us here. So let me just show you a multi-step problem where this would be helpful. You'll notice that we have multiplication problems and an addition problem, both combined here. So if I carry out the multiplication, 4.53 has 3 significant digits, 1.008 is 4 significant digits, so we need to round the final answer to 3 significant digits. I write down the value, and I know that I should have 3 significant digits in the answer, so I draw an overbar over the first 3 digits. But I keep at least 1 extra digit, because that will help to minimize the error at the end. So I had actually rounded off there to the thousandths place, even though I know that 6 is not significant. Let's carry out the next multiplication. Well, just like before, the first number has 3 significant digits. The final number has 4, so we need to round to 3 significant digits. So again, I draw an overbar over the first 3 significant digits, the 0.99 and the 1. And now when I add these together, assuming this is my final step, what I do is I add them, and then I look and I say, well, my last significant digit here was in the hundredths place, according to the overbar. And over here, my last significant digit was in the thousandths place. So which is least precise, hundredths or thousandths? Hundredths. So I round my final answer to the hundredths place. Now, the significant digit rules are good guidelines for doing proper calculations. However, these rules technically are superseded by some other procedures that we get into in the study of error analysis. Now, we're not going to get very in-depth with error analysis here, but I want to give you an idea as to where the sig-dig rules really wouldn't apply very well, where they would be likely to lead you to an incorrect error. So, in general, when we go ahead and look at a calculation, what we want is the final result to have about the same percent error as that of the least precisely known quantity. And generally by about the same. We want it to be, for example, if it's 0.1% in the least precise quantity, it should be on the order of 0.1% in the final answer. So let's go ahead and look at this calculation here. 9.92 times 1.035. If we go ahead and do that in the calculator, what we come up with is 10.2672. And if we follow the Signig rules, the answer we would get is 10.3. However, this kind of seems a little bit unsatisfying because that first number, 9.92, which went out to the hundredths place, has really been severely truncated. All of a sudden, we see it only going to the tenths here. And in fact, we're going to see that the 10.27 is the better answer according to error analysis. So how do we do this? Well, what we do is we say, okay, which of these numbers is the least precisely known quantity? 9.92 or 1.035? To figure out the least precise, we look at the decimal place. So the hundredths place goes only 2 places past the decimal, so it is less precise than 1.035, which goes 3 places past the decimal. So unless we're told otherwise, remember the uncertainty, the potential error, is going to be 1 of whatever that decimal place would be. So in the case of 9.92, that would be 0.01, so 1/100th, and we would divide that by the value, 9.92, and multiply that by 100%. So let's go ahead and do that. And what we get here is an error of about 0.1%, roughly. So now let's look at our answers here, 10.3 versus 10.27. With 10.3, the error would be in the tenths place here. So that would be 0.1 divided by 10.3 times 100%, which of course is going to be very similar to the answer that we would have had in the previous problem, except that it's going to be off by the power of 10. So 0.1 divided by 10.3 times 100% would be here 0.009, which times 100 is essentially 1%. On the other hand, the other value would be 0.01 over 10.27 times 100%. So we have here 0.01 divided by 10.27. And this gives me, let's see, about 0.09, which would round up to about 0.1%. So 0.1% is a closer error to that of the least precise value, 9.92. So even though the Signig rules would tell you that 10.3 is the better answer, 10.27 in this particular circumstance is going to be what does it for you. And we can kind of, if we look very carefully at calculations, we can know when to anticipate these issues. For example, in this case, 9.92, I know if I multiply it by a number that's just a little bit over 1, that's going to carry me from having 3 significant digits here into adding a digit into the tens place, which would look like it would have 4 digits here. And so that's the kind of scenario where when we're just going from a 9 over to a 1, or from a 0.1 down to a 0.09, where we're moving either the first significant digit or the last significant digit into a new decimal place, that these kinds of things are going to occur. However, we're not going to worry about this in this particular class. There are some calculations I might do where I say, well, I want to use the error analysis rules for what I'm demonstrating, but you're not responsible for knowing them in this class. Thank you, and I'll go ahead and continue on with studies of units of measurements in the next video.